Meteorology. Once the simple study of atmospheric events. Storms, hurricanes, tornadoes, and temperature changes, has grown in the 21st century to include such disciplines as atmospheric chemistry and physics, climatology, and global warming. In this program, we will present the principles of atmospheric dynamics. Look straight up at the sky on a clear, still day. What's there? If you didn't know better, you might think nothing is there. There is nothing to notice. Then off in the distance, the leaves on a tree move. Something is making the leaves move. Then on the horizon, clouds appear. Something is there after all. It's the Earth's atmosphere, an envelope of gases and tiny particles that surrounds the planet. Actually, an atmosphere is the most important thing for a planet to have. That is, if you wanted to have life like that found on our Earth. In our solar system, the Earth's atmosphere is unique among its celestial neighbors. The Moon, the object closest to the Earth, has no atmosphere at all, at least not that it can keep. A celestial body like the Moon is not big enough, doesn't have enough gravity to prevent atmospheric gases from escaping into space. The same goes for Mercury, the planet closest to the Sun. Interestingly, the side of Mercury facing the Sun is very hot, 660 degrees Fahrenheit. The other side is very, very cold, 290 degrees below zero. That's what happens when a planet doesn't have an atmosphere. It's the atmosphere that creates relatively constant daytime versus nighttime temperatures, like the temperatures found here on Earth. In our solar system, no atmosphere means no possibility of life. Venus, the planet between Mercury and Earth, has an atmosphere. A very heavy atmosphere composed almost entirely of carbon dioxide, that famous greenhouse gas. It turns out that the surface of Venus is also very, very hot, around 820 degrees Fahrenheit day and night. A toasty temperature that is the product of a runaway greenhouse effect. Mars, the red planet, the most studied planet in the solar system other than our own Earth, also has an atmosphere that is made up again largely of carbon dioxide. But unlike Venus, the atmosphere on Mars is very thin. In fact, its atmosphere is so tenuous that it actually changes in density with the seasons, growing in the summer and diminishing in the winter. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are quite different than the rocky inner four planets. They are called gas giants because their interiors are made up of gases and frozen gases like methane. Surprisingly, the Sun too has an atmosphere, although quite different than our own. Long before landing or crashing probes into the solar system's celestial bodies, astronomers were learning about their atmospheres using telescopes and a process called spectroscopic analysis. Indeed, for a long time, learning about celestial bodies in the solar system and in the universe was learning about atmospheres. Here at Kitt Peak National Observatory, that is just what they do. These techniques were also used to study our own atmosphere. What they confirmed was that our atmosphere was quite different from all the other atmospheres in the solar system. The major difference was an abundance of oxygen. You couldn't burn a candle in any of those other atmospheres. In fact, 21% of the atmosphere here on Earth is oxygen and 78% nitrogen. So the Earth's atmosphere has one very chemically active component, oxygen. Combine it with other elements, like iron, and we get rust, and one fairly stable component, nitrogen. Scientists would learn that these two components have a lot to do with life. What about the other 1% of the Earth's atmosphere? Well, most of that percent is argon, a little carbon dioxide, and the final part of that 1% is reserved for all the other gases, including water vapor. So what they also found was that the Earth's atmosphere had a structure divided into layers. It is common to say we live on the Earth, but really it would be more accurate to say we live in the Earth's atmosphere, like a fish lives in water. Where we live is in the lower, densest part of the atmosphere called the troposphere. Extending above the Earth's surface to 5 miles at the poles and 9 miles at the equator, the troposphere is what gives us those vivid, gorgeous sunsets. All weather takes place in the troposphere. Clear, warm days, rain, snow, storms, all of it. For those of us who fly on commercial jets, we often find ourselves leaving the troposphere for the lower reaches of the next atmospheric layer, the stratosphere. Up there, our pilots often report strong winds. Winds strong enough to affect the on-time arrival of their planes. The stratosphere is home to the jet stream. Looking like this on a weather map, it is a powerful band of winds known for bringing winter storms to the continental United States. The stratosphere is also home to the ozone layer, a peculiar kind of oxygen molecule that protects life on the planet from lethal ultraviolet radiation bombarding the Earth from space. Extending from 31 to 55 miles, the mesosphere starts where the stratosphere ends. Here is where most of those meteoroids streaking across the night sky burn up. Above the mesosphere is the largest section of the atmosphere, the thermosphere. If you have ever wondered where the northern lights or the aurora borealis are, the answer is, they're taking place in the thermosphere, perhaps as high as 300 miles above the ground. They shimmer and race across the night sky in flaming brilliance. Now, from bottom to top, the atmosphere, as one would expect, gets less dense. Fortunately for us, most of the atmosphere is right near the ground where we live. However, temperatures throughout the layers of the atmosphere are a different story. A graph of the temperature from bottom to top shows some quite unexpected twists and turns. First, it gets colder, then warmer, then colder again, and finally, very hot. This is because the atmosphere is in a delicate dynamic balance, a balance absolutely critical for all life on the planet. Understanding why this graph looks as it does demands that we understand the dynamic nature of the atmosphere. When it comes to life here on Earth, it is all about sunlight. Radiation from the sun transfers energy, heat, in waves, electromagnetic waves, to the planet. Some of those waves are absorbed. Think of pavement on a hot summer day. Some are scattered. Think of our own blue sky. And some are reflected. Think of light bouncing off a mirror. Radiant energy from the sun is virtually the only source, 99.9% of the energy available for movement in the atmosphere and the oceans, to heat and maintain temperatures in the lower troposphere so that life is possible. It is a delicate balance of trillions of heat transfers every second that makes it never too hot nor too cold for us. Indeed, the atmosphere is like a giant protective filter. It absorbs, scatters, and reflects solar radiation. As a result, only half of that solar output to the planet makes it to the ground. Starting from the uppermost layer of the atmosphere, we can see the critical role absorption plays in producing conditions favorable for life on the planet.
We can think of the atmosphere as a giant filter. We have a sphere covered by gas, and we have radiation coming in from the sun. And the most energetic radiation is in the form of X-rays and protons and other particles from the nuclear reaction in the sun. That hits the atmosphere, and it does a lot of chemistry and physics. The gases absorb that radiation, they're broken into atoms, they're turned into ions and free electrons and things like that. And that's in the outermost atmosphere. And that creates the ionosphere. And the ionosphere is nice because it's filtering out that energetic radiation so that it doesn't go down lower in the atmosphere.
So generating heat is what happens when solar radiation is absorbed by gases, liquids or solids. And remember that spike of heat right here in the troposphere? What's that about?
Lower down in the atmosphere, we have a layer known as the stratosphere, where there's now enough O2 molecules that they can absorb solar ultraviolet radiation and make ozone. And that ozone protects us from solar ultraviolet rays that would damage plants and also causes skin cancer and other problems for the biota down below.
What is interesting about absorption is that whatever absorbs the heat, whether it's desert sand in summer or gases in the atmosphere, they become new sources of radiation. They become smaller versions of the sun. For example, greenhouse gases are a big absorber of infrared radiation. Nitrogen is not.
Even with these filters, a lot of radiation makes it down to the ground, and we see that as visible light, and there's also some infrared radiation. And what that does is it warms the Earth's surface and the atmosphere closest to the Earth's surface. And as that gets warmed, it re-radiates infrared radiation, which is captured by the greenhouse gases that are in our atmosphere. And what this does is it creates a nice balance between radiation hitting the ground and radiation being absorbed to create temperatures that are conducive to life near the surface of the Earth.
Scattering is another phenomenon that occurs in the atmosphere. It happens when radiation is not absorbed by the gases and particles, but is scattered in all directions. Light, that part of solar radiation that we see, passes through the atmosphere. No absorption, but it does get scattered. Hence, blue skies and red sunsets. The last thing that might happen to solar radiation is that it gets reflected, pretty much back where it came from, that is, out of the Earth's atmosphere. Scientists have found that clouds, oceans, snow, and ice are marvelous reflectors of solar radiation, So much so that almost 34% of sunlight is kicked back out of the system. But that's not the end of the story when it comes to moving heat and energy around in the atmosphere. There are also conduction and convection. Put a pan of water on an electric stove. Turn on the burner and watch what happens. Soon the heat of the burner is transferred to the pan. It's transferred by conduction while the pan is in contact with the burner. The heat moves from the hotter to the colder object. Notice in the heat transfer, the pan does not move. Not so when the heat is transferred to the water. The water starts moving. And again, when the heat is transferred to the air above the pan, the air is moving. All this movement of heat is called convection. What atmospheric scientists have found is that all three kinds of energy transfer are always going on in the Earth atmosphere-ocean system. Somehow a heat balance is arrived at that keeps the relative temperatures in the lower reaches of the troposphere fairly constant and conducive to life. In many ways, it is a self-regulating system, like the way the human body maintains a constant temperature of 98.6 degrees Fahrenheit. Remarkably, the most important part of this story for us is that the troposphere is heated from the bottom to the top. In spite of being the furthest from the sun, the air closest to the ground is warmer than the air 5 miles closer to the sun. So the atmosphere regulates our atmospheric temperature. It does this by moving heat around. This moving of heat around in the troposphere is called weather. All weather happens in the lower atmosphere. The atmosphere also participates in a number of biogeochemical cycles that involve life itself, and, to an increasing degree, human and industrial activity. The best known is the hydrological cycle. The day starts with a bright blue sky. By mid-afternoon, water is evaporating from the surrounding ground in lakes. In the sky, clouds are forming. Early evening, a thunderstorm starts. Rain falls. Water fills nearby streams. This is the movement of water molecules, some of which will eventually reach the ocean. There, some of those same water molecules will once again evaporate into the atmosphere. And the process continues anew with the formation of new clouds. Each year, 16 million events like this occur, and at any given moment, 2,000 thunderstorms are happening across the globe. That's the simplified hydrological cycle. Water leaves the Earth as a gas through evaporation, sometimes forming clouds, and returns as a liquid in the form of rain, or as a solid in the form of snow or hail. The water in our planet forms a closed system. That is, the same finite group of water molecules has been here almost forever. Scientists like to say that most of these water molecules are in storage. 99% are in oceans, lakes, and streams, locked up in glaciers, or held in underground aquifers. The remaining 1% is in the atmosphere. Powered by solar energy, water is constantly circulating from one storage area to another through the hydrological cycle. One way to view that thunderstorm is, not only is it transforming water from one state to another, but it is transporting water from one place to another. Over time, this cycle of evaporation and precipitation reaches a dynamic global balance. This balance does not hold true for place, however. In some places, such as deserts and oceans, evaporation always exceeds precipitation. So there are other places on the continents that get the extra portion of precipitation. In times of stable climates, stable patterns of precipitation and evaporation arise across the globe. Other biogeochemical cycles that the atmosphere supports are the sulfur cycle, the nitrogen cycle, methane cycle, and the aerosol or particulate matter such as dust cycle. But the biogeochemical cycle that has become the most important for us today is the carbon cycle. Like the water molecules in the hydrological cycle, all the carbon atoms that exist now are the same carbon atoms that have always been. They show up in pure forms as diamonds, graphite, and most commonly, coal. And like water, carbon is found in reservoirs. The largest reservoir is in carbonate rocks, sedimentary strata from ancient oceans. But is also found as fossil fuels in the ground, dissolved in oceans, in the atmosphere as carbon dioxide, and in all living things. Indeed, there are more than 500,000 distinct carbon compounds in Earth's biosphere. But unlike water molecules, where physics drives the hydrological cycle, it is life itself that drives the carbon cycle.
The carbon cycle is one of the great biological geological cycles on Earth. So where carbon goes from carbon dioxide in the atmosphere and it's fixed by photosynthesis into organic matter, into life forms, and then it dies and is turned back by microbes into carbon dioxide again. Some of the carbon dioxide dissolves in ocean water and becomes part of ocean chemistry. And again, life will work on the carbon dioxide in the ocean water. It also occurs in lakes, incidentally, and will create life forms and organic matter with sunlight, and that will die. Some of it will sink to the bottom and will eventually be buried and become, over millions of years, oil. Similarly, on the land, you'll have swamps, which consists of leaves, branches, and just remains of what used to be alive, and it will be buried, and over millions of years will eventually turn into coal. And so when we burn the coal, we're actually helping to speed up the carbon cycle. So we're using what has been buried for millions of years, and instead of waiting for the Earth to bring these things back to the surface by natural processes of erosion and mountain uplift, where it would be slowly oxidized, we are speeding that up and just dumping all of this suddenly into the atmosphere, from where it will also go into the oceans.
Carbon dioxide is an odorless, tasteless, invisible gas. Once in the atmosphere, it is different than all other gases and particles put there by us humans. It has a long, long lifespan in the atmosphere.
Really, the basic problem with the carbon dioxide emissions that we are causing is that it doesn't disappear from the atmosphere-ocean system for thousands of years. So what we emit now will just accumulate. And whether it was emitted in 1880 or today or 100 years from now really doesn't matter all that much. It just builds up. because the natural processes of erosion and sedimentation that will return the carbon cycle to its pre-industrial condition, the timescale for that is 10,000 years. So in terms of our civilization and human lifespan and how far we can look ahead, it doesn't disappear. It's forever.
Interestingly, the smallest reservoir of carbon is in the atmosphere in the form of CO2. Yet without it, the Earth would be a frozen planet. Or, if there were a lot more, our world would be like Venus, too hot for life. That's not to say carbon dioxide concentrations in our atmosphere have not changed over the eons.
At the end of the last ice age, that's about 10,000 years ago, CO2 in the atmosphere was at a level, it was called 280 parts per million. So what that means is for every million molecules of air, there's 280 of them are carbon dioxide. Most of them are nitrogen and oxygen and argon and water vapor. And then comes carbon dioxide. Currently, the concentration is slightly over 380. So human emissions have increased it by slightly over 100 ppm. And currently the rate of increase is 2 parts per million per year. So in, say, 35 years, we could expect to have a concentration of, instead of currently 380, something like 450, if the rate of emissions remains constant, which is not likely. It's actually likely to go up. So it's likely to be faster.
So we see that the Earth's atmosphere is unique in the solar system. It has a distinct chemical composition that regulates solar radiation from the sun so that life is possible. But now that humans can interact with the atmosphere through the biogeochemical cycles, this interaction has changed the way the atmosphere regulates the heat coming from solar radiation, so that in the 21st century, understanding atmospheric dynamics is a major challenge for the survival of human populations.